I like to start by sharing some shocking news, which is that we cannot currently implement memcpy in the LLVM IR. If we consider a memcpy implementation in C, as you see here, we see that the copy is performed byte by byte using the unsigned chart type. This particular implementation is correct as it is backed up by the C standard, which says that any value may be copied into an array of unsigned charts, and we may access and manipulate the object representation of that value. This object representation is given by the set of bits that compose that particular value. So on the intermediate representation on the right, you can see that the loads and stores through the unsigned chart type are now represented, as you can see here, in loads and stores through the IH integer type. This invalidates the IR implementation, as the integer types in LLVM do not possess the same properties as the unsigned chart type. There are two main issues with the memcpy implementation. The first issue lies in copying padding bits, and the second issue in preserving pointer provenance across pointer copies. So I will now delve into each of these problems in more detail. So for the first problem, which lies in copying padding bits, we see here a structure, a C structure composed of a short and an int. As you might know, the short is 2 bytes wide, so the compiler is free to introduce 2 bytes of padding between these two fields in order to satisfy alignment requirements. Below, we see the definition of that same structure in the LLVM intermediate representation. As you can see here, the 2 bytes of padding are made explicit by the array of two 8-bit integer values. So currently, LLVM uses the poison value to represent padding bits, which constitutes the first problem with the memcpy implementation. So currently, integer values track provenance on a per value basis, which means that if we try to load the whole structure as an I64, as often occurs when performing load widening optimizations, we will load the whole structure as poison, even if a single bit of the 64 bits is poison, which is problematic as we'll copy the whole structure as poison and store it to memory. So to give a background on the second problem, which lies in copying pointers, I will now briefly introduce the concept of pointer provenance, which is not widely known. So, as some of you might already know, pointers in LLVM are not represented as plain integer values. These are represented by some additional metadata that is meant to be used to justify optimizations. So, we can represent a pointer as an object identifier and an offset value. Different allocations return a pointer which refers to an ununique object identifier. So in this particular example, we see two allocations given by the call to malloc, and these two allocations return two pointers P and Q. And as you can see, both P and Q are based on different objects, and therefore they get assigned a distinct object identifier. Furthermore, pointer arithmetic operations are set to preserve the pointer's provenance, only modifying the offset portion. In the example, you can see that adding both two pointers P and Q originate two different pointers, Pi and Qj, that maintain the same object identifier, but have distinct offsets. So, tracking pointer provenance has the main advantage of simplifying alias analysis, which enables other optimizations. In this particular example, we see stores through both pointers, Pi and Qj, and the compiler, seeing these two stores, is allowed to assume that the two stores do not alias with each other, as these pointers are based on different objects. So this is valid even if Pi and Qj end up having the same underlying address. So, as I already said, pointer provenance simplifies alias analysis, which can in turn enable other optimizations. Here in this example, we want to printf the value pointed to by pi, and as some of you might know, we could constant propagate the value in the store and directly print the value 1. This is only possible because we use pointer provenance to guarantee that the two pointers are based in different objects, and therefore we can perform this particular optimization. So the second problem with the memcpy implementation lies in preserving this provenance information across pointer copies. So currently in memory, LLVM IR has typed memory, meaning that we can distinguish between two types of bytes. The first type is a pointer byte, which along with a value holds this pointer provenance. All the other bytes can be thought of as an integer byte, which contains a numerical value. So currently, loading the current semantics of the IR defines that loading a pointer through an integer type in order to avoid casting the pointer to an integer and discarding this provenance, the load result is poison. So when we load a pointer from memory as an integer, the result is poison. So if we're trying to copy in memcpy a pointer value, we'll load the whole pointer byte as poison, as you can see here. So there's an alternative semantics currently being discussed, which was proposed by the Rust community, where instead of returning poison when loading a pointer through an integer type, we instead return a pointer with no provenance. This is good because the resulting pointer has no provenance and cannot be dereferenced, which means that it can only be used in comparison operations. However, even if we adopt these semantics, the current memcpy lowering is unsound, as we still discard the pointer's provenance. So our solution to this problem is adding a new type to the IR, which we call the byte type. This new type is able to represent the raw memory value as it is, being able to load both pointers and integers from memory without discarding the pointer's provenance. Furthermore, loads of paired values do not taint the load result, as the byte type can maintain and represent individual poison bits at bit granularity. So our plan is to also lower C and C++'s raw memory access types, which includes the character types and the C++ standard byte type to the byte type, as you can see here. This new lowering these types to the byte type, makes the lowering of the memcpy correct, as we're now storing a byte to memory and loading a byte from memory without introducing implicit casts. Our proposal also adds byte constants, which are needed to initialize global variables. These byte constants are strictly equivalent to their integer counterparts. So here we see a structure containing an int and a char field. On the right, you can see the corresponding LLVM IR, and this char field is mapped to the byte type, which is an 8-bit byte type, in this case a B8. And that constant, the constant C, is mapped to the byte constant 67. We also add a new byte cast instruction, which allows conversion of byte values to other primitive types. We allow two versions of the cast. So by default, the default version of the cast performs type punning, which it means that it reinterprets possible pointers as integers by discarding their provenance. We also allow a variant which does not perform type punning by specifying the exact flag, which returns poison if the type of the value held by the byte does not match the cast destination type. So in this particular example, if the load on the right loads a pointer byte, we're trying to cast that pointer byte to an integer type, and we will get poison as the integer type does not match that pointer type. So here we see a simple C function which adds a char value to the constant 1. Currently, LLVM unsoundly lowers this char value to an 8-bit integer. This 8-bit integer is then sign extended, the addition is performed, and then the addition result is truncated back to an 8-bit integer as required by the C standard. So with the byte type, now the char value is represented as a B8, value of the byte type. This byte type is then cast to an integer with the type punning variant of the cast, possibly reinterpreting pointers into their integral representation. Then the addition is performed as before, and then the truncation result is cast back to a byte as this function returns a char value. Furthermore, we also extended the truncate and logical shift-right instructions to accept byte operands. So this is beneficial to implement store forwarding optimizations. In this particular example, we store a byte to memory and then load it back at an offset. Instead of storing the byte and then loading it back again, we can instead shift the byte by 16 bits, then truncate the byte value to a single B8 value, and then reinterpret that as an integer through the byte cast instruction. It is important to note here that the truncation between bytes is needed, as if we did byte cast the bit 32 to an I32, we could spread poison bits if the bit 32 value originally contained either padding bits or pointer bits. So with a new type, as you can see previously, loads and stores were performed through the integer type, which had the problems of discarding pointer provenance and spreading padding bits. Now, the new lowering stores and loads these values through the byte type, which maintain the raw memory value without introducing implicit casts and spreading poison bits. Similarly, we now altered memcompare, because memcompare previously lowered the raw memory value as an integer value, which disabled pointer comparisons, as if we load the pointer as an integer, we cannot use memcompare to compare pointers because the load will result in poison. So similarly, now we load the raw memory value through the byte type, which does not introduce implicit casts and type punning, and then we cast the resulting raw memory value to an integer type performing type punning, which reinterprets pointers into their integral representation. This is beneficial because then the two pointers can be compared with the sub instruction. It is important to note that if we adopt the alternative semantics of returning poison, of returning a pointer with no provenance, instead of returning poison when loading a pointer through an integer type, we avoid changing this current memcompare lowing, which will be sound over pointer values. So another application of the byte type is in some unsound value coercions that are mainly performed today by GVN. So here in this example, we have two stores from the same memory location that typically happen in different branches, and GVN typically tries to merge these loads together. So on the left, we see an unsound coercion as the value of the pointer in B is replaced by a load of the integer, and then we cast the integer to a pointer through the into pointer instruction. As you might know, this is unsound, as if a pointer is stored in memory, the original program on the top will return that same pointer in value B, and the unsound coercion on the left, the value of A will return poison, and the value of B will itself be poison as well. So with the byte type, we can load the raw memory value without introducing implicit casts, and then we can use the byte cast instruction to cast it either to an integer or to a pointer, avoiding this implicit type punning. So we did implement this solution and benchmarked it using the Phoronix test suite, where we selected a set of 20 C and C++ applications, as you can see here. So for compile time, we did not observe any meaningful regressions, as this stayed between -1 and 1%, and most of these can be justified by statistical noise. Similarly, for runtime performance, we didn't observe any major regressions. For peak memory usage, it's the same story. This fit in a range of 0.5 to minus 0.5%. And for binary size, we initially did identify some regressions, which were mainly caused by loop vectorization differences in the cost model, which caused us to our version to vectorize some loops, which then extended code size. So I'm going to skip this slide because we're short on time. So we also implemented the byte type on LLVM and ran the LLVM over the LLVM test suite. We found that by introducing the byte type to the LLVM IR, we fixed the stats that were previously reported as unsound by Alive. So mainly these stats were caused by unsound lowerings of memcompare, memcpy to load-star pairs, and some of these tests were also caused by unsound value coercions, mainly performed by GVN. In conclusion, the introduction of the new type fixes long-standing issues in the LLVM IR, which now can represent raw memory values without introducing implicit casts. Furthermore, the new type enables the native implementation of various intrinsics such as memcpy, memmove, and memcompare. We also use the new type to fix existing unsound optimizations. These optimizations caused miscompilations in real-world C and C++ programs, and adding this new type lays a solid foundation for existing optimization passes to manipulate raw memory values. Our implementation spans across 2.6 thousand lines of code, which corresponds to roughly 0.05% of LLVM's and Clang's code base. So the byte type does not incur in any major performance regressions and constitutes a major step towards a more correct compiler. And thank you for your attention.
Thanks, Pedro. We have 5 minutes and even a little more for questions.
I've not checked recently, but I think as of last year, this explicit representation of padding was not consistent. Sometimes it is, sometimes it is not explicit.
Yeah.
I don't know if it's not related directly to your talk, but I don't know if you know the reason behind that and why it's made explicit at all.
Yeah, I don't really know the reason behind it, but I know sometimes it gets lower than zero initialize, I think, and sometimes it gets lower at poison bits, which makes sense because if we're emitting to real hardware, we might need to initialize it to some concrete value, therefore the zero initialize. But I can say that the current semantics implemented in Alive are that padding bits are represented as poison. Yeah.
And that cannot change easily. You know, it's like, for example, setting it to 0 or something is not facing some problems.
So I think that changing that to 0 would be a refinement. So I don't think that will introduce problems. So I think we can go from poison to 0 initialize if there's some strong will to do that. Yes.
Can you go back to slide 11 or no 14?
14.
Could those byte casts be exact?
It depends on the context, on the semantics we adopt for the load instructions. So there are, as I explained, there are two main semantics. So we either disallow type punning by returning poison when loading a pointer through an integer type, or we return a pointer with no provenance. So if we adopt the second semantics, I think the non-exact bytecast would fit here. So with the current semantics, yes, this bytecast would need to be exact. Yes.
So hello. Oh, yeah. On a C and C++ compiler with it's not just car and byte and such that can alias random types in the real world, although that's what the standard says. I was wondering if you had tested this with, like we have unions that allow arbitrary typecasts. We have no strict aliasing that allows you to do any, type punning you want. I was wondering if you had tested or implemented any support for all of those real world things the standard says you aren't allowed to do, but the actual code does.
Yeah, because I think what the standard says is that the unsigned char, signed char, and standard bytes can be used, can alias with any other pointer, can be used to access an object representation. That trick you mentioned about the unions and the type punning, I'm not really sure, but I think that's undefined behavior, so that's why.
So it's undefined behavior in the standard, but
in practice,
Clang and GCC both document this as a supported extension.
They emit the memcpy, I know, but we did not test it we just adhere to the standards. So we only support, we don't support unions, just char and signed char, the character types and standard.
So I guess, given that you observed no runtime performance difference, would you expect to see one if you emitted every load and store instead of just those as a byte type?
If we emitted...
Like every integer load, every size of integer, right? If I load an int from memory, if I do that as a byte type as well, not just the size, 1 byte loads and stores.
I mean, the byte type is meant to be used only if we want to preserve the raw memory value. If we
I understand that, but if I'm writing a memcpy, I might do that a word at a time. I might use an int, right, to load and store my pointers from memory if I, happen to know that it's more than 4 bytes. So, and real implementations of memcpy do this, even though it may not be strictly, via extensions or whatever, right? So, I guess the answer is no. You haven't tested that.
Yeah, we haven't tested, but we could test it. Yeah, but I don't know. I don't have any idea if it would have any impact.
Mm-hmm. Thanks.
Can you explain the difference between the pointer of the low buffer type and the pointer of the I8? What's the difference over there? I didn't get that part.
So I think I didn't get the question, but it was, what's the difference between loading a pointer?
The pointer of low bytes and the pointer of the I8.
Oh, okay. So the difference between loading a pointer through an I8 and through a B8. Right. So currently lowering a pointer through an I8, integer types do not track provenance information. So the current semantics is that when we load a pointer through an integer type, the result is poison. The byte type is more extensible as it can represent the pointer without discarding the provenance. So if we load the pointer as a byte, we have the raw memory value without implicit cast. So you have the pointer. If you use an integer type, you get poison.
So generally, remove the pointers.
Sorry, can you?
Generally, just remove the pointers in the memory.
Remove pointers?
Yeah, because you don't have the pointer in the memory with the pointer of the byte buffer, low byte, right?
So I didn't really get the question. It's remove pointers from.
I want to know, so when you are like doing the memory copy things, and actually because of you are using the pointer of the low bytes, so there's no pointer over there, so the copy will be like okay.
Yeah, the copy would be okay because the byte type can represent either pointers or integer values. Can represent anything that can be stored in memory.
Time for one more question.
I don't think it is.
All right. Possibly related to James's question, I was wondering if you had looked into only using a byte type, and so like eliminate the integer type or give it the semantics of the byte type. Was that? Yeah, go ahead.
So that's a common proposed solution, but we cannot do that because we need integer types. We cannot simply get the integer types and extend it to be a byte type, because then we would extend provenance information to integers as well. And that would ruin alias analysis, because when we load something as an integer, we might be loading a pointer. And therefore, we also would disable integer optimizations, because if you have an integer I and add it to 0, if I and 0 have different provenance, we can fold it to I, for example. So that would have a major performance cost. So we need both bytes and integers.
Yeah, if there's no more questions, let's thank Pedro again.
Thank you.